Welcome to The Explainer. Today we are diving deep, and I mean deep inside the Earth, to understand the engine that drives our entire world. We're talking about everything from the slow, unstoppable drift of continents to the incredible power of volcanoes. And it all boils down to this epic, planetary-scale battle between calm and chaos.
I mean, think about it for a second. We live on this rock that is constantly moving. Mountains are being pushed up, continents are literally sailing across the globe, volcanoes are erupting. All this action on the surface we see is really just a symptom. It's a sign of a much, much more powerful engine running deep inside the Earth's mantle. So the real question is, what's driving it?
Well, to get at that answer, we first have to understand this really fundamental conflict in physics. It's basically a tipping point, a moment where a system can suddenly flip from one state of being to a completely different one. And in this case, it's all about the two ways heat can move. One is calm and orderly, and the other, well, the other is churning and chaotic. Okay, so let's get into it. On one side of the ring, you've got conduction, and on the other, you've got convection. These are our two main contenders in this fight over heat, and figuring them out is the absolute key to unlocking the secrets of what's happening inside our planet. So let's break these two down. First up is conduction, the calm one. You know this already. Picture putting a metal spoon in a hot cup of coffee. The handle gets hot, right? But the metal itself isn't moving. That's conduction. Heat is just passing from one molecule to the next. Now, convection, that's the chaotic state. Think about boiling a pot of water. The hot water at the bottom literally rises up, and the cooler water from the top sinks down to take its place. You get this churning motion. The fluid itself is moving and carrying the heat along with it. Right, so here's the kicker. A fluid isn't stuck in one mode or the other. It can actually flip, and what makes it flip are these tiny, random little wobbles and disturbances that are always present. In that calm conduction state, those little wobbles just fade away. But if you push the system to a tipping point, those same tiny disturbances suddenly start to grow and grow until they trigger a total flip from calm to chaos. And that idea of a trigger, of a tipping point, brings us to the core of this whole thing. Physicists figured out that this flip from conduction to convection isn't just random. No, it's actually decided by a fascinating cosmic tug-of-war between a bunch of competing forces. So on one side of the rope, you have the forces that are trying to get things moving, the drivers of convection. The big one is buoyancy. Hot fluid expands, it gets less dense, and it wants to rise. Simple as that. And gravity gives it a helping hand by pulling the cooler, denser fluid down to replace it. But pulling on the other side of the rope are the brakes. You've got viscosity, which is really just a fluid's internal stickiness that resists all that motion. And then there's thermal diffusion, which is trying to just even out the heat, without anything moving at all. It's the force that favors calm conduction. So, how do you know who wins this cosmic tug-of-war? Well, scientists came up with this incredibly elegant way to keep score. It's called the Rayleigh number. You can just think of it as the final score in the battle. It brilliantly combines all those driving forces and all those braking forces into one single number that tells you instantly if that fluid is going to churn or if it's going to stay put. And for a simple, idealized layer of fluid, that tipping point, that one magic number where everything changes, is 657.5. It's a surprisingly specific number, isn't it, for something so fundamental to how the universe works. Here's how it works. If the Rayleigh number for a system is less than that critical value, less than 657.5 in our perfect little setup, then the brakes are winning the tug-of-war. The fluid is stable. Any little disturbance just fizzles out, and heat just moves calmly and quietly through conduction. But the very moment that Rayleigh number ticks just past 657.5, everything changes. The drivers, buoyancy and gravity, they overpower the brakes. The whole system becomes unstable. Now, the slightest little wobble doesn't die out. It grows, it amplifies, and the fluid just erupts into this chaotic, churning convection. The system has officially flipped. And, this isn't just a theory. The whole concept was first hammered out by Lord Rayleigh way back in 1916. He used a really simple model of just a layer of fluid being heated from below. But as you can imagine, the real world is just a little bit more complicated than that. It turns out that number, 657.5, is for a very specific, very idealized situation. And as scientists started playing around with it, they quickly realized that if you change the conditions, you change the tipping point. The tug-of-war is still happening, but the score you need to win suddenly changes. For example, that original 657.5 number, That's for a fluid where the top and bottom surfaces are free slip, meaning it can just slide around without any friction, like water on oiled glass. But what if the boundaries are rigid, like water in a metal pan where the fluid kind of sticks to the edges? Well, suddenly, the brakes get a huge advantage. You have to push the system way harder to get it to boil, and the critical Rayleigh number jumps all the way up to over 1700.
So this all brings us to the main event. How does this concept from a laboratory apply to the mind-boggling scale of our own planet? We're not talking about a thin layer of fluid in a pan anymore. We're talking about thousands of kilometers of molten rock. And this is where the story gets really good. Back in 1931, a geologist named Arthur Holmes made this incredible intellectual leap. He took this abstract physics concept of the Rayleigh number, and he applied it to the Earth's mantle. And he proposed that this exact mechanism, convection, was the engine powerful enough to move entire continents across the face of the planet. At the time, it was a completely radical idea, and it took decades for people to really accept it. Which, of course, leads us to the ultimate question. If a number somewhere around 1700 is enough to make a fluid in a pan start to boil, what's the score for the battle that's happening right now, deep beneath our feet in the Earth's mantle? The estimated Rayleigh number for the Earth's mantle is somewhere around 3 billion. Just let that sink in for a moment. Not 3,000, not 3 million, 3 billion. This is what geophysicists call a highly supercritical state. And that's really just a technical way of saying that the system isn't just a little bit past the tipping point, it has blown past the tipping point and left it miles and miles behind in the dust. So what that incredible number means is that the tug of war inside our planet, it isn't even a contest. The driving forces of buoyancy are literally millions of times stronger than the braking forces of viscosity. The mantle isn't on the verge of convecting, it is in a state of constant, unbelievably vigorous, chaotic convection. Our planet is, for all intents and purposes, boiling. But of course, the story doesn't end there. Knowing that the mantle is wildly supercritical was a huge step, but it was really just the beginning. Now, scientists are building these ever more sophisticated models to truly understand the nitty-gritty details of our planet's engine. That simple model of a fluid layer got us to the main point, which is amazing. But to get a really accurate picture, scientists have to account for all the unique and complex realities of what's actually happening inside a planet. And the models they're building today they're mind-bogglingly complex. They have to factor in things like how minerals literally change their crystal structure under the crushing pressures deep inside the Earth. They have to figure out how much heat is coming from radioactive decay inside the mantle itself versus how much is coming up from the core. And they have to grapple with the fact that this is all happening in a spherical shell, not a flat box. Each one of these details adds another crucial layer to our understanding. And this all brings us to one last really cool thought. The same physics that governs a pot of boiling water on your stove and the massive engine inside our own planet, it applies everywhere in the universe. So as we look out at other rocky planets and moons, we have to ask ourselves, which of them have also crossed their own tipping point? What other worlds out there are hiding a roiling, convective, and maybe even a living fire deep inside?